Welcome back to Meissa 2.0, where curiosity lights the path and the universe opens its arm to those who seek. I'm Rameshka Kanagaraj, and it's my pleasure to guide you through it another night of cosmic wonder. Brought to you by Astronomical Society, University of Colombo. Tonight marks the second session of this enlightening series, a journey where science doesn't just answer the question, but dare to ask deeper ones. Among the stars, balance hold the key to their brilliance. As we gaze into the skies, we often forget it's not a choice, but the balance that keeps those stars shining. It's with the great excitement that we welcome our speaker for the evening, Mr. Ravindu Kalhara, holding BSc honors in computational physics and currently serving demonstrator at the Department of Physics and former treasurer of Astronomical Society. Mr. Kalhara is a well in both language of cosmos and the elegance of equilibrium. Tonight, he will step into the concept that lies at the very heart of stellar existence, hydrostatic equilibrium of the stars, the very balance that prevents a star from the collapsing in one itself or bursting into the pieces. So, get ready into the dive deep into the mechanism that keep our sky glowing. Stay curious, stay inspired, and without further ado, please join me in welcoming Mr. Ravindu Kalhara. Over to you, sir.
Okay, thank you, Rameshka, for your nice introduction. Okay, let me share my screen. I hope you guys can see my screen, right? Okay. First of all, thank you, Astronomical Society, for giving me for giving this opportunity for me to do a session about hydrostatic equilibrium of stars, right? So let's get into that our session, right? Right. Today topic is hydrostatic equilibrium of stars, right? So if we consider stars in our universe, we know there are different type of stars, right? So like main sequence stars, red giant stars, and also white dwarf stars, neutron stars. There are different type of stars, right? So the key question is how these stars maintain their structure, right? What are the mechanism? What is the mechanism behind the structural stability of these stars, right? So this question is can be explained actually by the this hydrostatic equilibrium of stars by this concept, right? So that is a very brief introduction what I'm going to talk about in this session. So basically in this session I'm talking about this mechanism, how the hydrostatic equilibrium, what is hydrostatic equilibrium, how this hydrostatic equilibrium maintained in stars, what are the contributors to this hydrostatic equilibrium, right? So those are the concepts that I'm going to talk about in this session also, right? So that's a brief introduction about this session, right? So let's get into the content of this session, right? Okay. All right. In this session, I have to say that to build a model, I'm going to build a model to explain this hydrostatic equilibrium, right? To build here, I'm only considering a very simplistic model based on different assumptions. You will see what are the assumptions that I'm going to take to build this model, right? I'm going to build a model to explain how this hydrostatic equilibrium happens and what is hydrostatic equilibrium, right? So for that, here, as the first assumption, I'm considering a spherically symmetric star, right? Spherically symmetric star, right? So in this spherically symmetric star, right, I'm considering a shell which is lies at a distance r. You can see at a distance r from the center of the stars, right? So the thickness of the star, the thickness of this shell is basically dr, and I'm here taking the density of the material inside this shell as rho, right? As rho, right? So now in this shell, I'm going to consider a very small volume element. You can see here. I'm here considering the forces acting on this small volume element, right? The first force acting on this very small element is the gravitational force, obviously gravitational force. That gravitational force basically exerted by the material inside this R sphere, the sphere which has R radius, like in this inside sphere, right? So by this mass, there's a gravitational force act on this small element. So this part, this force can be written like this. You can see this expression, right? So this part, I'm here representing the force act on this small element as this, and I'm integrating over azimuthal and the polar angle in order to build the shell, as I explained previously, right? So from that, by some simplification, we can come up with this part, right? So the mass contained within the system, within the sphere, which has r radius, given by this expression, right? So this is the force exerted on this shell, spherical shell, which located at r distance, right? So that is the gravitational force. So we know if there is only the gravitational force act on this shell, there's a gravitational collapse because there is no any other mechanism or any other force to balance this force, right? But that is not the case in our normal stars, because those stars are existed. So that means there should be a separate thing that can be contributed to balance this gravitational force or to prevent this gravitational collapse. So that force is created by the pressure, right? This is the important part here. So that pressure, the net force acting on the shell due to the pressure can be written like this. This is the expression for the pressure, net pressure exerted on the force due to the pressure exerted on the shell, right? So you can see there's a pressure gradient over here, right? This is the really important case here, right? So the pressure gradient is the key component that provides this force, right? So this is the basic what are the forces acting on this shell, right? So let's get to, right. So then we can apply Newton's second law for the shell, right? So this is the total, the resultant force acting on that shell, right? This is the mass in that shell, right? So from that, by some simplification, we can arrive to this expression. This expression tells us the acceleration of this shell, right? But to maintain the equilibrium, to maintain the structural stability, there should not be a acceleration. So that means in order to maintain the hydrostatic equilibrium, this acceleration should be 0, right? So that means at the end, this hydrostatic equilibrium can be defined like this. Hydrostatic equilibrium is when the resultant force act on the shell becomes 0. When the resultant force acting on this shell becomes 0, we call that hydrostatic equilibrium of a particular star, right? This is general derivation, right? All right. So finally, with that concept, with that idea, this r double dot becomes 0. So we can get this expression, right? But the problem is to describe this system completely, we should have a knowledge about this pressure, right? So without this pressure, our knowledge about this system is limited, right? So that is the main point that I'm covering in this session. What are the contributors of this pressure function? That is the idea. That is the key point that I'm going to address throughout this session, right? Right. As I said, to fully describe the hydrostatic equilibrium, the pressure function should be known, right? So, and also we call this pressure function as the state equation of state, right? So, to develop a simplistic model for this pressure, right? I'm going to make another couple of assumptions also, right? First one is the, as I mentioned here, we know in normal star, a normal star made of plasma, like our sun, right? You know, normal star. So those are basically made of a plasma, ionized hydrogen and the helium. Basically, those are the main contributors for that plasma, ionized electron and the ions, right? So, but to build this simplistic model, what I'm going to do is I'm going to assume that, right? I'm going to assume that the thermal energy of the particles is sufficiently large than the potential energy, than the energy created due to the interaction of the particles, right? The thermal energy of the particles is sufficiently large than the potential energy between particles, right? That means we can think that these interactions, this potential energy due to the interaction is negligible compared to the kinetic energy of the particles, thermal energy of the particles, right? So with that, we have a very nice system, right? here we have to only consider about the kinetic energies with this assumption, right? So this is really important to build a simplistic model, right? Right. That is the first assumption, right? Assuming that the potential energy due to the interaction of the particle is negligible, right? That's the first assumption. Then another important assumption is local thermodynamical equilibrium, right? So what is the local thermodynamical equilibrium? So we know star is not an equilibrium system, right? Why I'm telling you that? Because if we consider a star, the surface of a star, the temperature of the surface of a star is normally in thousands of Kelvin. I can't exactly remember the value, 6,000 or something like that in Kelvin, right? But in the core, it is really high temperature. The temperature at the core of a star, normal star, it is really high. I think about 10 to the power 7 Kelvin, like that, right? So you can see there's a large pressure, large temperature difference there. So that means this whole star not in a thermal equilibrium in globally. Globally, it is not in thermal equilibrium. So, but according to this assumption, what we are going to do is we are considering a region in the star. The dimension of that region is really small compared to the dimension of the star. Yeah, here I'm going to consider a region which has dimensions. The dimension of that region is really small compared to the dimension of the whole star, right? So in this region, I assume that in this region, our star is in thermal equilibrium, right? In this small region, right? So that means we can develop a model, we can develop a simplistic model based on the thermal equilibrium ideas, the concept related to the thermal equilibrium, the pressure, especially the pressures, the pressure of the equilibrium system, thermal equilibrium system. From those ideas, we can build a model because of this locally thermodynamical equilibrium assumption, right? So, which means even though we have thermal equilibrium in the local system, our entire model can be built like that thermal equilibrium varies as a function of radius, right? So we can define temperature, density, like thermodynamical parameters as a function of radius, as a function of the distance from the center to that area, right? So that's the another most important assumption here, local thermodynamical equilibrium, right? So with all these ideas, as I explained previously, I'm here considering spherically very nice spherical symmetric star. From that, I came up with these differential equations, and here I'm taking a little bit more assumptions to build a simplistic model. With that, as I said, I'm going to consider build the equation of states. So with these ideas, in order to build this pressure function, there are three types of pressures that can be contributed to this pressure function. Right? First one is ideal gas pressure. we know that ideal gas pressure, but here's the another pressures, radiation pressure and the degeneracy pressure, which can be contributed to this entire pressure function, right? So now I have some idea, some assumptions, and I came up with three contributors to this pressure function, right? First one is, as I said before, ideal gas pressure. This ideal gas pressure obviously varied because of this first assumption, right? And also the second assumption. We know the ideal gas law. This is the ideal gas law, right? So, and if we consider the material inside a star, it is basically ions, especially protons, because ionized hydrogen, and the helium nuclei, and the electrons, ionized electrons, electrons due to the ionized hydrogen and helium, right? So those are the content in the plasma, in the gas, right? So if we consider only the ideal gas pressure here, this ideal gas pressure can be think of that contribution for different partial pressures which are created by these ions and the electrons, right? So this is the expression that I came up with. So here I define what are the N-ion and Ne terms, right? So here I take a summation over different species, right? So, and this is the draw is the obvious, as I said, this is the density of the material, right? So Xi is the mass fraction of a particular species, like as an example, mass fraction of hydrogen, mass fraction of helium, right? So, and that is the Ni, right? So Ni means basically, if you consider this ideal gas pressure law, this N represent number of ideal gas particles contained within a unit volume, right? Same idea for this also, right? So however, finally we arrive with a pressure function which is depend on density and the temperature, and this part basically represent the composition, right? So different composition, right? That means mass fraction or different ions or whatever. This part basically represents the composition. So if you consider the ideal gas pressure in this simplistic model, it is a function of these terms, right? So that is the ideal gas pressure. So next question is, what stars can be explained by this ideal gas pressures? What kind of stars, right? So to get that idea, we can consider this graph, right? So if we consider our sun type stars, low mass stars, its pressure can be considered as the main contributor of the pressure function, or the equation of star, equation of state, main contributor of the equation of state as the ideal gas pressure, right? In the low mass stars like our sun, right? So here you can see this graph basically shows the variation of temperature with respect to density, right? You can see our sun, there's a line. This line basically represent, as I said, the local thermodynamical equilibrium. So this is only valid for locally, right? So if we move around inside the star, the density and the temperature varies, right? But if we consider the ideal gas pressure in this region, according to that assumption, that varies like this line represent that is different position has different temperatures. So finally, we can represent that case like this, right? So you can see there are other stars which has high mass and the low masses. We can talk about those stars later in this session. So there's an important thing I forgot to mention. This graph represent this graph shows for our sun the composition. We consider as I said, this pressure is a function of composition also, right? We have to draw a graph like this. We have to set this part fixed, right? So that means I set that composition similar to our sun, right? So this X 0.7, the mass fraction of hydrogen in our sun, and this XE, XHE, the mass fraction of helium of our sun, and the other part, and the other ion mass fraction, right? For this composition, we can obtain this graph, right? So that is the importance of ideal gas pressure. This ideal gas pressure is the main contributor to the pressure function or the equation of states in especially in low mass stars like our sun, right? But you can see here when the mass increases, this line move to this region. So what is this region, right? So this region is the region where the main contributor is radiation pressure. All right. So for massive stars, so the stars with significantly large mass, other than the ideal pressure, radiation pressure also plays a significant role, right? So now let's talk about the radiation pressure. So first of all, we have to understand how this radiation pressure created. So radiation pressure basically created by the photons, right? So how these photons form? These photons are formed, as I mentioned here, basically from the nuclear fusion, right? We know that for every star, every normal stars that we are considering, there's a nuclear fusion process in our mainly in the main sequence stars. The main nuclear fusion process is PP chain. We know that, right? So these nuclear fusion processes create a large amount of photons. Right? So these photons can create a radiation pressure, right? So to build an expression that represent the radiation pressure, we have to go with the Bose-Einstein statistics, because photons are bosons, so they should follow the Bose-Einstein statistics. So based on that, this here I represent the equation for the probability of occupying a particular energy level by a boson under equilibrium conditions, here local thermodynamic equilibrium, right? So this is the probability of occupying particular energy level by a boson, right? This function represented that. So and again, we have to go with the quantum mechanics, right? Because here I'm considering about the Bose-Einstein statistics, right? So according to the based on the quantum mechanics, especially based on the particle in a potential box, 3D potential box model that we are normally discussing in quantum mechanics, we can came up with a function, what we call density of states. Right? So here I represented that. So this G function is the number of allowed quantum states in a unit volume with the momentum in the range P to P plus dP. Right? So this deriving this formula is a different story, but basically this function represents the number of states, number of quantum states available in the system to occupy by the bosons here, because I considering in the boson. Right? These are the available states, right? But to estimate, to get an expression for the occupied states, that means the states that are occupied by the bosons, right? We have to define another function, this NP function. This NP function we call momentum distribution function in a unit volume. So basically this NP function represent, especially this NP dP part, this represent the number of particles per unit volume with momentum in the range P to P plus dP. All right. So this function can be expressed by the Bose-Einstein statistic function and the density of states function here. Right? So with some simplification, we can arrive this expression. Right? Here it is important thing I have to mention here. Right? You can see in the Bose-Einstein statistics formula, we can see mu part here. This is what we call chemical potential. Here, the chemical potential is 0 because these are bosons. These are non-interacting bosons. Right? And also they are the number of bosons in a closed system, not conserved number of bosons in a closed system. So based on that, we can say this mu is 0. Right? So with that, and also here this GS is what we call Londe G factor. All right. So this GS represents the number of intrinsic quantum states, right? Number of intrinsic quantum states. So if you consider a photon, right, this GS become 2. The reason for that is there is a 2 polarization direction for a particular photon. Right? So that means there should be a 2 independent quantum state for a particular photon. So therefore, this GS become 2. So with that idea, with that detail also, using this expression you can be used to estimate the number of particle in a unit volume here, in consider whole volume, right? So here's the pressure function. So using this expression, we can come up with this final expression, right? 1/3 A to the power 4. So you can see the radiation pressure is a function of temperature, right? So as I said before, in a massive stars, in other than the ideal pressure, this radiant pressure plays a significant role. So with that, we can again rewrite a new expression for a massive stars, a new expression for equation of states by considering this radiation pressure also. But finally, we have a equation of state which is depend on density, temperature, and the composition, right? So that's for the massive star. So let's get back to the graph that I showed before. Right? So here, previously I explained this ideal gas pressure region. All right. In this radiation pressure region is the pressure that I derived here is the most significant contributor for the pressure in if that star in this region, right? So here this line, this boundary represented where the radiation pressure equals to the normal ideal gas pressure, right? So as I said, this model, this ideal gas pressure plus radiation pressure model works for massive stars, right? Here you can see a star which has a mass 100 times of our solar mass and the 10 times of solar mass. So you can see when the mass of the star increase, the radiation pressure, the significance of radiation pressure in the equation of states is increasing, right? So here in this region, you can see for this temperature and the density, the main contributor is radiation pressure, right? So that's the idea, right? So this is the model, the equation of state that we can derive for the massive stars by considering ideal pressure, ideal gas pressure, and the radiation pressure. So as I explained previously, there's another type of pressure also. The degeneracy pressure, right? This degeneracy pressure, you can see the region for that degeneracy pressure lies within this area, right? So this boundary represent where the ideal gas pressure equals to non-relativistic degeneracy pressure, this boundary from this point to this point, this is that boundary, right? You can see that works for low mass stars, right? So let's see why. So degeneracy pressure, that degeneracy pressure always arises for fermions, right? So that means we have to go with the Fermi-Dirac statistics to get an expression for the pressure, degeneracy pressure, right? Here I shown the Fermi-Dirac statistics formula, right? So it's also representing probability of occupying a particular energy level by fermions. Previously, I shown in the Bose-Einstein statistics, it's for bosons. This is for fermions, because right under equilibrium conditions, right? It's given right here. And also same thing here. You can see the density of states function here. So by evaluating this part, we can get the number of fermions per unit volume with momentum in the range P to P plus TP, right? So this is again same type of function that I shown previously, right? So this is the expression that I can arrive with some simplification. So then again, as I said, I'm here considering degeneracy pressure, right? So we have to define what is degeneracy pressure means, right? So here I plot the Bose-Einstein statistics graph, right? The variation of probability with respect to different energy states, right? So you can see when the temperature varies, the shape of the shape of the function also varies, right? So whenever temperature reaches to 0 Kelvin, the function become like this. From the 0 to this highest energy value, this as I represented here, this mu up to this point, from here probability become 1 and other part becomes 0 for this case, right? So what does that T approaches 0 means, right? When the temperature get reduced, the kinetic energy also reduced, right? So that means these fermions try to occupy same energy states, but the fermions should agree with the Pauli exclusion principle. So that means there cannot be two fermions that are occupied by a same energy state, right? So but the temperature reduced, they try to occupy same state, but it cannot happen. So because of that, even at the 0 Kelvin, there is a energy in this fermions, right? So that's the point. That's the way of achieving degeneracy pressure, because they have some energy, some kinetic energy, even though they are in 0 Kelvin, right? So the pressure resulting from the energy of fermions in the degenerate state, this degenerate state is the way when the T approaches to 0 Kelvin, right? So the pressure resulting from the energy of fermion in the degenerate state is called degeneracy pressure. So at the 0 Kelvin, this expression reduced into this part, right? Here up to PF, this PF is the Fermi momentum. Up to that momentum, the NP, this distribution function, is given by this expression, right? Other part for above the momentum above this Fermi momentum is 0. This distribution function becomes 0, right? So this is the degenerate state, right? This is the distribution function for degeneracy state, right? But here I derived this for 0 Kelvin, but how this thing valid for stars, right? This is I derived for 0 Kelvin, right? Right. So in stars, the way of achieving this degeneracy is different, right? That's the important thing that you have to understand, right? So let me give a very simple explanation how this thing happened, right? So if we consider stellar gas, the material inside the star, right? Stellar gas, that stellar gas, as I said, it contains electrons and ions, right? So when you consider the de Broglie wavelength of electrons and the ions, especially here, because we are considering in the fermions, I'm here talking about only the fermionic ions, like hydrogen nucleus, it's a proton, it's a it should be a fermion, right? The stellar gas, especially the electrons, when you consider the de Broglie wavelength of those fermionic ions, right? Fermionic ions and the electrons. If we consider the mass of these ions and the electrons, the mass of electrons is really small compared to the fermionic ions, right? So that means whenever the density of a star is sufficiently high, right? Sufficiently high, the mean separation between the particles, especially the electrons, mean separation between the electrons approaches to the order of de Broglie wavelength, right? So when the density increases, the mean separation between electrons, especially electrons, their separation become to the order of de Broglie wavelength. Therefore, that means, right? That means because of the mass difference, the de Broglie wavelength of electrons should be higher than the de Broglie wavelength of fermionic ions, right? So that means, as I said, when the density increases, the mean separation between particles becomes order of electron first, right? I would say first, because their de Broglie wavelength is higher than the fermionic ions. So that means when they becoming, the mean separation becoming into the de Broglie wavelength, order of de Broglie wavelength region, they become degenerate. So that's the way of achieving degeneracy in the stars, right? Especially this degeneracy pressure, we talk about degeneracy pressure, especially in white dwarf stars, right? So because white dwarf stars come at the end of the life cycle of a star, right? At that time, the nuclear fusion ends at the end of the life cycle. So that means there are only ions and the electrons contained within the space within the star without energy source, right? Without energy source. Energy source is, we know, the nuclear fusion, right? So because of that, there's no way of balancing. There is no way of additional pressure to balance the gravitational collapse. So because of the gravitational collapse, these white dwarf stars, the density in the white dwarf stars increase until the electrons become degenerate. So that's why in the white dwarf stars, the degeneracy pressure is the main contributor in the equation of state, right? Here I derive the degeneracy pressure, expression for degeneracy pressure for electrons right? So for that, I used this expression that I've used previously also. This expression, right? By using that expression, I able to derive an expression that explains the degeneracy pressure, right? So here you can see the degeneracy pressure is only a function of density, right? So in the white dwarf stars, right? In the white dwarf stars, this pressure, the force created by the pressure only generated by this degeneracy pressure, right? So that's the way of balancing the gravitational collapse, that gravitational force in white dwarf star, right? So that's the final contributor. We consider different type of star. Here I mainly consider the white dwarf stars, right? This is the way of balancing. This is the way of maintaining the hydrostatic equilibrium in a white dwarf star, right? Because of the degeneracy pressure, right? So at the end, the same diagram that I showed previously, right? So I said previously, this represents the ideal gas pressure equals the degeneracy pressure, right? So here I would say I here consider only about the non-relativistic degeneracy pressure, right? So that's the way of maintaining the hydrostatic equilibrium in different stars, right? Here I start with a simple model, right? I first consider a spherically symmetric star. Then I came up with a couple of assumptions, right? From those assumptions, I consider only about the equation of state, that pressure function, right? So that is the whole content of my session, right? So here I basically explain how we can understand the structural stability maintain over the time by a star based on the pressure and the basically based on the pressure, right? So if we consider more detailed solar models, here as I said, the pressure function, the function that I considered here is a function of rho t and the composition. We can get another relation, some more relations for this density, temperature, and the composition, right? If you consider much more in detail solar models, here basically what I did was I built a simple model, a simple solar model which explains the hydrostatic equilibrium of different stars. I'm not considering only just one type of stars, right? So that's the whole presentation that I intended to present here. All right. So these are the reference, and thank you for everyone for joining to this session. Right. If you guys have questions, put your question in the chat box, so you can unmute the mic and ask the question, right? So thank you for everyone coming to this session. Right. If you guys have questions, put in the chat, or you can speak up and ask the question. Right. Why did you use the cylindrical shape? All right. Here, let me go to the first slide here. Here, this is just a illustration, right? This is not actually cylindrical shape. If you consider this volume element, this is not a cylindrical shape. This is just a illustration here. The actual volume element, if you consider the spherical coordinate system, the volume element is different, right? Let me write the volume element. We consider volume element in spherical coordinate system, right? R squared sine theta. dr d theta d psi, right? So this is the volume element, right? Here this is just an illustration, right? So you can see here I just use the, here you can see it right here, right? This is actually not a cylindrical shape. This is a little bit different in shape if we consider shape, but shape is just not actual matters here, because here I consider the volume element associated with spherical coordinate system, right? So I think I gave a good answer for that. Here, this is just an illustration, right? This cylindrical shape is just a representation, not the actual shape, right? So I'm just going to, after this decrease, yeah, a path to go to astronomical side. Oh, is there something related about my actually I think here that question asked by Meissa. I'm sorry, I cannot give a good answer for this, because I'm basically a very newbie in this field. Actually, I just graduated 1 month ago, right? 1 or 2 months ago, I think. So I'm not really experienced person in this field, how the paths changes over time, what are the paths in various universities or various countries. I'm not very familiar about those cases. So the problem is I cannot give you a good answer for your question, because I have no very good idea about this section, because I am a very just graduated. I have no very I'm not a well experienced man in this field. So I'm sorry about that. So if you want more ideas about your question, much more details about it, you can contact our Dr. Janaka or Professor Chandana. They are well experienced people in this field, so you can contact them, right? So I'm sorry, I cannot give a good answer for this question. right? So then the model is site similar to what we do to prove. So then the model is site is similar to what we do to prove the Biot-Savart law in magnetic field. I'm not entirely clear what is the question, but I think you are asking about model site is similar to what we do to prove the Biot-Savart. Here's the thing. In the classical electrodynamics, to explain the magnetostatics, we use this Biot-Savart law. So actually, in this session, as I said, these stars, if we consider our sun-like stars, they are basically made of plasma, right? So they are charged particle in there. So they are moving around because of the kinetic energy, right? So they create magnetic field, they create electric field. But in this model, as I said, I haven't considered all these things. Look at the assumption that I made, right? I neglect all the interaction between particles, right? So if to create magnetic field or to create electric field, there should be charges, right? So if there are charges, these particles interact with each other, electrostatic repulsion or the forces due to magnetic field exerted on different particles, right? So, but based on that assumption, I made an assumption the kinetic energy of particles is sufficient to neglect those interactions, right? I made that assumption to simply to make this model very simple, right? So there are a lot of models. There are models that consider these magnetic field effects, especially the models which are deal with the magnetohydrodynamics, right? So those models deal with those interactions also, but here I just consider only the simple ideal pressure, radiation pressure, and the degeneracy pressure, just to make our model very simple, right? So I think I'm not entirely sure I gave the answer for your question, because I'm not very clear about your question also, right? So that's the idea, right? If we consider a normal star, normal means our sun-type stars, means sequence stars. When think about a situation like this, what happened if our sun-type star get contracted, a little bit contracted, right? So that means, according to the virial theorem, the internal energy should be increased, right? Internal energy increases means the kinetic energy of the particle increase, right? With that, the fusion rate increase, right? So with the increase of fusion rate, it generates more energy. Then again, if there's a compression, because of the newly generated energy, this again get stabilized. This again go to initial state, right? So that's what happened, right? So there is a, if we explain this hydrostatic equilibrium in that way, also we can explain this hydrostatic equilibrium in that way also, if we consider the virial theorem, right? So that that's there is a fission acceleration if there is if there's a contraction in the volume due to the gravitational collapse, right? but it's fusion. The fusion, the rate of fusing protons, that's the point, that's the thing get increased, right? Not the fission, right? Okay, so are there any questions?
What do you mean by increasing the rate?
Rate means nuclear fission rate, right? So nuclear fission rate, when the star get little bit contracted, the temperature increase. So the kinetic energy increase. With that kinetic energy, there is a the probability of fusing protons increase. So that's how the rate, the fusion rate increase, right? So that's what I mean there, right? Right. So again, because of the increase of this fusion rate, there's more energy generation. Because of the more energy generation, again, according to virial theorem, the volume of the star should again increase, right? So in that way also, we can explain the equilibrium of star, right? According to based on the virial theorem also, right? So it's kind of different than what I explained in this session, right? Are there any questions?
Yeah, I have a question, Ravindu.
Yeah.
So when you came up with these derivations and this simplified model, how much of the standard literature did you have to leave out for the sake of simplicity?
Leave out means?
No, you mentioned that there are many other effects that are going on, but you considered only very few. So how much, like, yeah, could you like describe how much of it you had to neglect, or is it all those effects negligible in a like value, yes, purely value, like the magnitude, just by the magnitude, or are there conceptually things that you had to neglect for this simple model?
Yeah, here's the thing. There are a lot of things that I neglected in conceptually also, because especially the interaction, the electrostatic, electrodynamic interaction, right? So by this model, I cannot explain, other than the hydrostatic equilibrium, I cannot explain magnetic field, or right, the solar flare. So that sort of phenomenon I cannot explain just by using this model. This model I built only to explain, only to get an idea about how these stars structurally stabilized, right? There are a lot of things that are neglected. I agree with that, right? There are a lot of things that I cannot explain here, but this model is sufficient to explain this hydrostatic equilibrium, right? So there are plenty more other models. So especially if we consider there are type of stellar models like polytropic models. polytropes. So those polytropes model again came up with a different model. They, according to those model, the pressure equation of states only depend on the density, right? According to polytropes, right? It's again a model. So actually, it's agree with the degeneracy pressure also, right? As I shown previously, the degeneracy pressure depend on the density also, only density, right? Even in the polytropes, the equation of state, consider that equation of state depend only on the density. That case, that assumption fit with the some another case, especially wide dwarf stars, right? Again, with that, we can derive the Chandrasekhar limit also, right? This Chandrasekhar limit basically, by considering this polytropic model, we can derive Chandrasekhar limit, that is the upper limit of a wide dwarf stars, right? In that model also, they only consider the density, but it fits with some stars, right? So these models built to explain certain cases in a star. Here, the things that I explained just to explain the hydrostatic equilibrium. Other than that, it is not sufficient. That model that I explained here is not sufficient to explain other phenomena, right? So I think I gave some good answer for your question.
Yes, thanks. And also, are there stars that are less complicated by observations that we can apply this model directly to rather than going for the more complicated ones?
Yeah, our sun, the low mass stars. So our sun is really the describing the pressure inside the our sun-like stars. It is really good agreement with this model also, right? So if you go to this diagram, you can see it's basically the variation of pressure completely lies within the ideal gas limit, ideal gas region, right? So to explain the density, to explain the hydrostatic equilibrium in our star-like stars, this model is really sufficient, right? So, and also this model is actually good enough to explain the massive stars also, but I'm not entirely sure how much this model fit with those, but to explain the hydrostatic equilibrium, just to get an estimation, I think this model is also sufficient for those stars, but mainly our sun-like stars, this model is really good to explain the hydrostatic equilibrium, right? I'm not considering the values that I getting from this model. The situation, the equilibrium can be explained using this model, right? Hydrostatic equilibrium.
Right, and is explaining the equilibrium of a star necessary for understanding other properties like maybe luminosity or yeah, such effects? So is it important that we model the star as accurately as possible, or is this hydrostatic equilibrium modeling just done for the study of that phenomenon?
Right. This derivation basically focused on is hydrostatic equilibrium. If you go to the luminosity or that kind of case, this model is not sufficient to explain that that phenomenon, because the reason for that is there are many unknown variables in this part, in this model also, right? This temperature is the key point that we, if we consider the luminosity of a star, temperature is the key component, right? If we go with the much more in detailed model, that consider a model that consider the luminosity also, especially the photon flux across the surface. I think that model is good enough to explain that kind of scenarios, right? So, but this derivation is, I think, just good enough, only good enough to explain the hydrostatic equilibrium, right? So I think that's the answer I can give you.
Yeah, thanks. And just for my curiosity, I'm asking, what were your challenges when compiling this information? I know you first prepared it for your Sigma article. So what were the challenges in referring all those sources and compiling it into a simple explanation that you have presented here? How far is the material in the reference material, like reference sources from what you have presented here? Did you have to make your own simplifications, or was it already done available to you likewise?
Right. This is actually, I did some part in this to write the that article. I did some calculation, but I don't think they are the things that I have. I'm the person that first done. I don't think like that. If I go to your first question, the challenges that I faced here. So this is the idea of, especially because of you mentioned about the article. The idea of writing that article is come from after doing the statistical mechanics course, right? So in that course we discussed about the degeneracy pressure, right? So starting from that, I studied a little bit more how the stellar modeling done in current astrophysics, current field, right? So I found a couple of references, right? So in those references, they mentioning this scenario. They are basically explained based on the material that I referred. In those references, they mentioned some models like polytropes, which is used to explain the hydrostatic equilibrium, right? So based on that also, from that idea also, and I found a couple of another resources that are considering the ideal gas pressure in especially our sun, right? So by considering all these sources, based on all these sources, I wrote that article, right? After writing that article, I did this session obviously, right? If I think about the challenges that I have faced, I can't exactly remember what are the challenges. So key challenge is to mapping these ideas, how we can find, how we can use these ideas, this ideal gas pressure, and the degeneracy pressure and the radiation pressure, or everything related to thermodynamics, thermal physics, and the statistical physics, right? So these ideas, these are the core ideas that talk about in those fields. The main challenge is how can I map those ideas with the stars based on the material that I have referred, right? I think that's the key challenge that I faced in there. How can I match all these things to write an article, to make an article, to make this kind of presentation, right? I think that's the challenge that I faced. So I think I given somewhat good answer.
Yeah, thank you very much.
Again, there's another question. Could you explain the diagram? I think he's referring about this diagram. I think here, this part, right? Right. Okay. This is the this diagram. As I said, the equation of state basically depend on the temperature, pressure, and the composition. Right. In this graph, I basically shows the variation of temperature and the density, right? To plot that two variables, I have to fix the composition. So first I fix the composition that match with our sun, match with our sun based on. So after fixing the composition means these values, right? So then for that composition and the equation of state, which only contributed by one of the pressures that I will explain, right? That means this region, the prominent pressure is radiation pressure, and the ideal gas pressure is this region, right? So these boundaries represent where the pressure of these two type of pressures get equal, right? This boundary shows that thing. So this boundary, same thing, right? So we can derive that by just use this this expression. You have an expression for D gas, like over here. Like over here, right? And that equals to this part. So from that I can get this straight line in the log scale, right? This is log scale. You can see this is in log scale. So basically by using this expression, I can get this straight line in the log scale, right? So same thing done for this part also, right? So then these lines represent if we consider point in a star, as an example, I consider our sun, point inside the star. At that point, there's a density at that point, right? And also temperature at that point. And I move that point over the inside of the star. So I get variation of temperature and pressure. So that's what I plotted over here, right? So this is basically come from the local thermodynamical equilibrium, right? Right. So that's what I plot. These are the other type of masses, different stars that has different masses. These, right? So that's the basic. That's the thing represent in this graph. I think you get an somewhat good idea about this. Part. Could you explain the diagram, right? Okay. Right. I think time's up. Okay. Rumeshika, right there.
Thank you so much, sir, for that insightful session. Before we proceed, I kindly invite everyone to switch on your webcams. We take a moment to capture this beautiful memory with a group photo. Guys, everyone, if you are in a comfortable position, please turn on your camera.
The video sharing is blocked.
Thank you, everyone. Now, I would like to take a moment to express our gratitude to everyone. First and foremost, a sincere thank you to Mr. Ravindu Kalhara for enlightening session with us and expertise on the hydrostatic equilibrium of the stars. Your passion and clarity truly help us in appreciate the cosmic forces at the play of universe. To our dedicated organizing team at the Astronomical Society of University of Colombo, thank you so much for making second session of Meissa 2.0 a smooth and stellar experience. And the most importantly, to each and everyone who joined this evening, thank you for being a part of Cosmic Journey. Your presence and curiosity make it even more meaningful. We hope to see you all again in the upcoming session. Until then, stay curious, stay inspired, and never stop looking up. Have a wonderful night.